Hello. I'm going to go through the OCR 2022, A-Level, Chemistry, Paper 3, Unified Chemistry. If you find this video useful, please click like, and leave a comment, as it will help me to carry on making more videos like this. In the fixed comment under the video, I leave a link to my website jctnotes.com where you can see the written answers to this paper. Question 1 contains questions from different areas of chemistry. In Part A, we have that ammonia and ammonium nitrate are compounds of nitrogen. In the first question, we have that the boiling point of ammonia is -33 degrees Celsius and the boiling point of ammonium nitrate is 210 degrees Celsius. We are asked to explain why there is a large difference in boiling points. The ammonia is formed by discrete molecules that interact between each other by weak intermolecular forces, whereas ammonium nitrate is an ionic compound with strong electrostatic forces between the ions. Ionic bonds require more energy to break than intermolecular forces. In the second question of Part A, of Question 1, we have that two students discuss the oxidation numbers in ammonium nitrate. One student claims that the two nitrogen atoms have the same oxidation number. The other student disagrees and claims that the nitrogen atoms have different oxidation numbers. We are asked to explain, with reasons, which student is correct. Ammonium nitrate can be considered as a combination of ammonium ion, NH4+1, and nitrate ion, NO3-1, each of these ions contain nitrogen. We start with the ammonium ion. Each of the four hydrogens contribute with a positive charge, therefore, the total contribution of the four hydrogens is +4. The ion has a total charge of +1. This means that nitrogen neutralizes 3 positive charges, and its charge is -3. In the nitrate ion, each or the 3 oxygen contribute with a negative charge of -2, giving a total charge of 3 times 2 equals to 6 negative charges. The ion has a total charge of -1. This means that nitrogen neutralizes 5 negative charges, and its charge is +5. The student that considers that the nitrogen atoms have different oxidation number is right. In the ammonium ion the nitrogen has an oxidation state -3 and in the nitrate ion it has an oxidation state +5. In Question 1, Part B, we have the mass spectrum of a sample of brass, an alloy of copper and zinc. The peak at m/z equals to 63 is from the copper 63 and the peel at m/z equals to 65 is from the copper 65. The remaining 4 peaks are from isotopes of zinc. In the first question, we are asked what are the percentage compositions of copper and zinc in the brass sample. If we add the percentage of copper 45.64% plus 20.36% we get 66%. The percentage of the zinc can be calculated as the difference between 100% and the 66% contribution of the copper, that gives 34%. You can also find the answer by adding the peaks of the zinc from the spectrum, that gives also 34%. In Question 2, we are asked to calculate the relative atomic mass of zinc in the sample of brass, giving the answer to 2 decimal places. The results from Question 1 indicates that given 100 grams of brass, 34 grams are going to be zinc. To calculate the relative mass of zinc, we multiply each percent of zinc by its mass and divide by the total mass of zinc, that is, 34 grams. I get 65.42. In Question 1, Part C, we are given the structure of an organic compound, with 4 protons labeled 1 to 4. In the first question, we are asked to fill a given table with the splitting pattern of the proton NMR spectrum. In the proton NMR, the splitting pattern of the hydrogen atoms attached to one carbon is going to be determined by the number of protons in the adjacent carbon atom, and it is given by the formula n+1, where n is the number of protons in the adjacent carbon. Let's start with the proton 1, the next carbon is the one that has the proton 2 with 2 protons, therefore the proton 1 is going to be n plus 1 equals to 2 plus 1 equals to 3, giving a triplet. Moving to proton 2, the next carbon with protons is due to proton 1, with 3 protons. This means that the proton 2 is going to be n plus 1 equals to 3 plus 1 equals to 4, it is a quartet. Moving to proton 3, the next carbon with protons is due to proton 4, with 1 proton. Then, the proton 3 is going to be n plus 1 equals to 2 plus 1 equals to 2, it is a duet. Moving to proton 4, the next carbon with protons is due to proton 3, with 2 protons. Therefore, the proton 4 is going to be n plus 1 equals to 2 plus 1 equals to 3, it is a triplet. In question 2 of this section, we are given the chemical shift of protons 2 and 3 and we are asked to suggest why the peaks for proton environments 2 and 3 have the chemical shifts shown in the table. The shifts are typically referred to the tetramethylsilane or TMS. This molecule shows a high electron density around the proton. When the proton is attached to more electronegative environment, say to an oxygen, the electron density around the reduces. The lower the electron density around the proton, the higher the shift. In the case of proton environment 2, there is one adjacent carbon attached to an oxygen, whereas in the case of proton of environment 3, it is attached to 2 adjacent carbons, each attached to an oxygen, reducing the electron density in greater extent and producing a greater shift. Part D, of question 1, is about glycine. In the first question, we are asked about the hydrogen-nitrogen-hydrogen angles of 2 salts from the glycine, sodium glycinate and glycine hydrochloride, and why the angle are different. In the case of sodium glycinate, the angle is 107 degrees, with a structure in which the nitrogen has 3 bonds and 1 lone pair of electrons. In the glycine hydrochloride the angle is 109.5 degrees with a structure in which the nitrogen have 4 bonds, 3 sigma bonds and a coordinate covalent or dative bond. The lone pair of electrons provides a greater repulsive force than the coordinate covalent bond, reducing the angle. We move to the second question of Part D, of question 1. Glycine reacts with aqueous copper-2 ethanoate to form copper-2 glycinate and ethanoic acid. Copper-2 glycinate is a complex which exists as 2 square planar isomers. We are asked to write an equation for the reaction and draw the structures of the 2 square planar isomers of the complex. As the formula of the glycine is given in the previous question and the formula of the copper-2 glycinate is also given, the reaction should be easy. The structure is planar and the ligand is bivalent. One ligand is a coordinate covalent bond from the lone part of the amine group, NH2, to the copper, and the other is a copper-oxygen bond from the carboxylic group. The isomers are going to have the same ligand next to each other or in the opposite side. Question 2 is about redox reactions. Section A is about calcium hypochlorite, CaClO2, that is prepared by reacting chlorine gas with calcium hydroxide in excess as per given equation. In the first question, we have that 420 cubic decimeters of chlorine, measured at room temperature and pressure, is reacted with an excess of calcium hydroxide. The solid products are dissolved in water to form 4 cubic meters of solution. We are asked to calculate the concentration of calcium hypochlorite in the solution, giving the answer in mole per cubic decimeter, with the appropriate significant figures and in the standard form. At room temperature and pressure, 1 mole of gas has a volume of 24 cubic decimeters, so, 420 cubic decimeters are 17.5 mole. From the stoichiometry of the reaction, we know that 2 mole of chlorine produces 1 mole of calcium hypochlorite, therefore, 17.5 mole of chlorine produces 8.75 mole of calcium hypochlorite. As the volume of the solution is 4 cubic meters, or 4,000 cubic decimeters, the concentration of calcium hypochlorite is 2.1867 by 10 to the power of -3. As the problem gives the number in 3 significant figures, we round the answer to 3 significant figures as 2.19 by 10 to the power of -3. In the second question of part B, of question 2, we have that when calcium hypochlorite is heated, it decomposes to form calcium chloride, CaCl2 and calcium chlorate, CaClO32. This is a disproportionation reaction. We are asked to write an equation for this decomposition and explain, using oxidation numbers, why this is a disproportionation reaction. Disproportionation or dismutation is a redox reaction where one compound is oxidized and reduced in the same reaction. The reaction that we have is calcium hypochlorite produces calcium chloride and calcium chlorate. To adjust the equation, I will use the algebraic method. Let's fix the calcium hypochlorite to 1, and call A, the number of mole of calcium chloride, and B, the number of mole of calcium chlorate. Using the calcium, we have 1 calcium from the reactant, calcium hypochlorite, that will provide A atoms of calcium for the calcium chloride and B atoms of calcium for the calcium chlorate. This gives the equation 1 equals to A plus B. Focusing on the chlorine, we have 2 chlorines from the reactant, calcium hypochlorite, that will provide 2 times A atoms of chlorine for the calcium chloride, as each calcium chloride has 2 atoms of chlorine, plus 2 times B atoms for the calcium chlorate, as each calcium chlorate also has 2 atoms of chlorine. This gives the equation, 2 equals to 2 times A, plus 2 times B. Finally, we focus on the oxygen. From the reactant, we have 2 atoms of oxygen that will give to 2 times 3 times B atoms of oxygen for the calcium chlorate. This gives the equation 2 equals to 6 times B. From the equation of the oxygen, we find that B equals to 1 divided by 3. Using this value in the calcium equation, we get 1 equals to A, plus 1 divided by 3. This gives A equals 2 divided by 3. This will give that 1 mole of calcium hypochlorite produces 2/3 of mole of calcium chloride and 1/3 of a mole of calcium chlorate. To avoid fractions, we multiply by 3 and have as equation, 3 mole of calcium hypochlorite produces 2 mole of calcium chloride and 1 mole of calcium chlorate. To explain the disproportionation, we need to refer to the oxidation numbers of chlorine, as it is the chlorine which changes its oxidation number. We start with the calcium hypochlorite. The calcium has a total contribution of +2. Each oxygen has a contribution of -2, as we have 2 oxygens. The total contribution of the oxygen is -2 times 2 equals to -4. The calcium and the oxygen leave a total contribution of 2 negative charges. As the calcium hypochlorite is neutral, these 2 negative charges are going to be neutralized by the 2 chlorines. Each chlorine has an oxidation state of +1. In the calcium chloride we have that the calcium has an oxidation state +2, that are neutralized by 2 chlorines. That means that the chlorine has an oxidation number -1. In the calcium chlorate, the calcium has a total contribution of +2. Each oxygen has a contribution of -2, as we have 6 oxygens, the total contribution of the oxygen is -2 times 6 equals to -12. The calcium and the oxygen leave a total contribution of 10 negative charges. As the calcium hypochlorite is neutral, these 10 negative charges are going to be neutralized by the 2 chlorines. Each chlorine has an oxidation state of +5. Then, the explanation is, the chlorine with oxidation number +1 in the calcium hypochlorite has been oxidized to oxidation number +5 in the calcium chlorate and reduced to oxidation number -1 in the calcium chloride. In Part B, of Question 2, a student analyzes 3 redox reactions. The student concludes that different ions containing chromium can act as oxidizing or reducing agents. We are asked to explain why the student is correct, using the terms oxidizing agent and reducing agent, ideas about electrode potentials and equilibrium, and including overall equations. Electrode potentials are used to predict the direction of redox equations. A redox reaction is going to be favorable in the forwards direction, left to right, if the potential difference is positive. If it is negative, the favorable direction is the reverse reaction, right to left. We are provided with 3 equations. I will number them in the order that they are given, equation 1, 2 and 3. The equations are typically provided as reductions and we need to manipulate them accordingly. Chromium only appears in equation 2. So we need to combine equation 2 with the other 2 equations in such a way that the total potential of the reaction is as positive as possible. We start with equation 1 and equation 2. We can see that if we change the direction of equation 1, we change the potential from negative to positive. If we compare the number of electrons in both equations, we have 2 electrons in the first equation and 6 electrons in the second equation. To equalize the number of electrons, we multiply by 3 the first equation. Careful, the potential is not multiplied, as it is an intensive property, and it does not depend on the size of the system. When both equations have the same number of electrons, we add them. We have electrons and protons as common terms in both sides of the equation. If we start with the electrons, we have 6 in each side, therefore we can cancel them. We move to the protons. On the left we have 14 and on the right we have 6. Cancelling 6 protons on both sides, we get 8 protons on the left. If I rearrange the equation a bit and we get, as the potential is positive, this reaction is favored left to right. The chromium is reducing, therefore, it is acting as an oxidizing agent. We now focus on the equation 3. As the potential of the equation 3 is greater than the potential of equation 2, we change the direction of reaction 2 to obtain a positive potential. If we change the direction of equation 3, we will finish with a negative potential. Comparing electrons, equation 2 has 6 electrons and equation 3 has 3 electrons. To equalize electrons, we multiply equation 3 by 2. In the resultant equation, we cancel common terms. These are electrons, protons, and water. We start with the electrons, they are 6 in both sides, therefore, we cancel them. We continue with the water, we have 7 molecules of water on the left and 8 on the right, we can cancel 7 of them and leave 1 molecule of water on the right. We finish with the protons, we have 16 on the left and 14 on the right. We can cancel 16 of them, leaving 2 on the left. Rearranging the equation, we get, as the potential is positive, this reaction is favored left to right. The chromium is oxidizing, therefore, it is acting as a reducing agent. We can see that the chromium can act as oxidizing or reducing agent. In Part C, of Question 2, we have that a student bubbles hydrogen sulfide gas through an acidified solution containing manganate 7 ions. A redox reaction takes place, forming aqueous manganese 2 ions, a yellow precipitate and 1 other product. We are asked to construct the equation for this reaction. State symbols are not required. We start by writing the information given. Hydrogen sulfide plus protons and manganate 7 ions producing manganese 2 plus yellow precipitate and other product. To identify the yellow precipitate and 1 other product, we have to make an informed guess of what these are. The information that we have is: first, as reactants we have atoms of hydrogen, sulfur, manganese, and oxygen. Second, we have a redox reaction, where the manganese changes from an oxidation number +7 to an oxidation number +2, that means that it has been reduced. As we have a reduction, something needs to be oxidized, probably the sulfur. In the hydrogen sulfide, the sulfur has an oxidation number of -2, that could be oxidized to elemental sulfur, with an oxidation number 0 and forming a yellow precipitate. As we have a redox reaction with oxygen and hydrogen atoms, it is probably that the other product formed is water. We can suspect that the reaction is hydrogen sulfide plus protons and permanganate ions producing manganese 2 plus sulfur plus water. We need to adjust the equation. We start with the half reactions. Half reactions. Reduction, permanganate to give manganese 2 plus. Oxidation, hydrogen sulfide to give sulfur. We balance the oxygens by adding water. In the reduction reaction, we have 4 oxygens as reactant. To equalize these, we add 4 molecules of water as product. We balance the hydrogens. In the reduction reaction, we have 8 hydrogens due to 4 molecules of water as product. We add 8 protons as reactant to equalize these. In the oxidation, we have 2 hydrogens provided by the hydrogen sulfide as reactant. We equalize these by adding 2 protons as product. We move to balance the charges. In the product of the reduction, we have 1 negative charge due to the permanganate and 8 positive charges due to the 8 protons, giving a balance of 7 positive charges. In the product we have 2 positive charges due to the manganese 2. To equalize both sides, we add 5 electrons to the reactants. In the products of the oxidation reaction, we have no charges. In the products, we have 2 positive charges. To equalize both sides, we add 2 electrons to the products. Next step is to equalize charges in both half reactions. In the reduction we have 5 electrons and in the oxidation we have 2. Therefore, we multiply the reduction by 2 and the reduction by 5 and both half reactions have the same number of electrons. Adding both equations. Cancelling common terms, electron and protons. Therefore, the answer is, 2 mole of permanganate reacts with 5 moles hydrogen sulfide gas and 6 moles of protons to produce 2 moles of manganese plus 2, 5 moles of sulfur and 8 moles of water. In question 3, we are given a table with the melting and boiling points and densities of 1-bromobutane and butane 1-OL. A student prepares a sample of 1-bromobutane by refluxing 9.25 grams of butane 1-OL with sodium bromide and sulfuric acid. After reflux, the reaction mixture is purified. The student obtains 6.1 cubic centimeters of pure 1-bromobutane. In Part A, we are asked to draw a diagram to show how the student would have carried out the reflux, to calculate the percentage yield of 1-bromobutane and to describe how the student could have obtained pure 1-bromobutane from the reaction mixture obtained after reflux. The basic distillation equipment includes a condenser with water inlet at the bottom and expelled at the top, a boiling flask where the sample is placed and heated, a Bunsen burner or suitable source of heat. Calculation of the yield. The synthesis reaction that we have is butane 1-OL plus sodium bromide plus protons to obtain 1-bromobutane. This means that 1 mole of butane 1-OL gives 1 mole of 1-bromobutane. The molecular mass of butane 1-OL is 4 times 12 plus 10 times 1 plus 16 equals to 74 grams per mole. If we divide the initial 9.25 grams by this molecular mass, we get 0.125 moles of butane 1-OL. With the given density on the table, we can find that 6.1 cubic centimeters of 1-bromobutane is 7.7348 grams of 1-bromobutane. The molecular mass of 1-bromobutane is 4 times 12 plus 9 times 1 plus 79.9 equals to 136.9 grams per mole. If we divide the mass by the molecular mass, we get that we have 0.0565 mole of 1-bromobutane. With the number of moles of butane 1-OL and 1-bromobutane, we can find that the yield is 45.2%. The purification is performed in a separating funnel, by separating the bottom layer, as the density of the bromobutane is higher, therefore it will be at the bottom. The bottom layer should be dried with an anhydrous salt, like potassium chloride, magnesium sulfate, or sodium sulfate. The final step is to distill at 102 degrees Celsius, boiling point of the 1-bromobutane. In Part B, of Question 3, we are asked to show the steps of the mechanism of the reaction of butane 1-OL with sodium bromide and sulfuric acid to form 1-bromobutane. The mechanism is a nucleophilic substitution and take place in two steps. In the step 1, the oxygen atom of the alcohol group accepts a proton to form a positively charged intermediate. In the step 2, bromide ions react with the intermediate from step 1. With the information given is very easy to draw the mechanism. In the step 1, we have that the lone pair of electrons is shared with a proton, creating an positively charged intermediate. In step 2, the marking scheme allows two possible options. In the first option, the bromide ion attacks to the carbon and breaks the carbon-oxygen bond. In the second option, the carbon-oxygen is broken first and the bromide ion attacks the positive charged carbon. Question 4 is about a given equilibrium. Two students observe the evolution of the reaction at different temperatures, 50 degrees Celsius and 90 degrees Celsius, and we are provided with a plot of the absorbance, related of the pink color of the product, over time. Using the graph and the relevant chemical theory, we are asked to explain the difference between the different initial rates at 50 degrees Celsius and 90 degrees Celsius and predict the sign of the change in enthalpy of the reaction. At 90 degrees Celsius, the initial rate, given by the gradient in the graph, is faster, indication of more frequent collision and that more particles have greater activation energy. It also reach faster the equilibrium state, where the absorbance tends to stabilize to a fixed value, indicating that the concentration of the pink complex is kept constant. When the equilibrium is reached, the concentration of the pink complex at 90 degrees Celsius is lower than at 50 degrees Celsius. This indicates that the reaction is exothermic and therefore the change in enthalpy is negative. In Question 4, Part B, the students investigate how the addition of aqueous silver nitrate affects the equilibrium. 4.1. We are provided a graph with the equilibrium concentrations before and after of the silver nitrate addition. In the first question, we are asked why the chloride ion drops after the addition of silver nitrate. The chloride forms a precipitate of silver chloride with the silver. The reaction of precipitation with silver nitrate is used to identify halogens. In the second question, we are asked to explain the changes in the concentration of the differences species after the addition of silver nitrate, referring to the equilibrium. 4.1 in the answer. The concentration of the water-cobalt complex increases and the concentration of cobalt-chlorine complex decreases in the same proportion. The concentration of chlorine ions increases 4 times more than the variations in concentration of the water-cobalt and the cobalt-chlorine complexes. Equilibrium. 4.1 shifts to the right. Question 5 is about energy changes. A student plans to determine the enthalpy change of hydration of calcium ions. We are given the lattice enthalpy of calcium chloride and the enthalpy change of hydration of chloride ions in a table. We are provided with the method that the student follows. We can summarize the method saying that the student measures the maximum increase in temperature of water when calcium chloride is added. We are given data to calculate the masses of water and calcium chloride and the increase in temperature. We are asked to calculate the enthalpy change of solution of calcium chloride and determine the enthalpy change of hydration of calcium ions, showing our work, including an energy cycle linking the energy changes. We assume that the density and specific heat capacity of the solution are the same as for water. As the question is long, I will address it in steps and clear the space as we progress. I will start with the enthalpy change of solution of calcium chloride. The enthalpy change of solution is the energy absorbed or released when 1 mole of an ionic solid dissolves in sufficient water to form a very dilute solution. In our case, from the experimental data, we know that after dissolving the calcium chloride, the temperature of the solution has increased by 39.5 minus 21.0 equals to 18.5 degrees Celsius. As the reaction is exothermic, the temperature has increased, the change of enthalpy is negative, we will add the sign at the end. The mass of solution is 127.84 minus 21.24 equals to 106.6 grams. As we assume that the density and the specific heat capacity, C, of the solution are the same as for water, we can find in the data sheet from the exam that C is equals to 4.18 joules per gram and Kelvin. We can calculate the enthalpy, change in heat energy of the solution at constant pressure, using increase of heat equals to the mass of the solution times its heat capacity time the increase in temperature. Replacing the data that we have, I get that the enthalpy is 8.2434 kilojoules. As the reaction is exothermic, we can say that this value is negative, minus 8.2434 kilojoules. However, this quantity refers to 27.45 minus 18.17 equals to 9.28 grams of calcium chloride. We need to change to kilojoules per mole. The atomic mass of the calcium chloride is 111.1 grams per mole and 9.28 grams of calcium chloride is 0.08352 mole. If we divide minus 8.2434 by 0.08352, we obtain that the enthalpy change of solution of calcium chloride is minus 98.7 kilojoules per mole. Result that we will need to answer the enthalpy change of hydration of calcium ions. I will clear in a moment what we don't need and keep this reaction and its enthalpy. To find the enthalpy change of hydration of calcium ions, I need the results of the table and the enthalpy change of solution of calcium chloride, removing the rest. The enthalpy change of hydration is the enthalpy change when 1 mole of a specified gaseous ion dissolves in sufficient water to form a very dilute solution. In the case of calcium, we are given the lattice enthalpy of calcium chloride. The lattice enthalpy is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. In the case of calcium chloride, we are also given the enthalpy change of hydration of chloride ions. The enthalpy change of hydration is the enthalpy change when 1 mole of a specified gaseous ion dissolves in sufficient water to form a very dilute solution. In the case of calcium chloride, we have 4 equations. I'm going to put them in a table and copy it in a new slide. Sorry, but it is getting messy on the computer. As equation 1, I will use the one that we are looking for, the enthalpy change of hydration of calcium ions. As equation 2, we have the lattice enthalpy of the calcium chloride. As equation 3, we have the enthalpy change of the hydration of chloride ions. And, as equation 4, we have the enthalpy change of solution of the calcium chloride. I will now copy this table in a new slide to continue. We need to get the equation 1. We see that the ion calcium in form of gas as reactant in equation 1, also appears as reactant in equation 2. The aqueous ion calcium that appears as product in equation 1 also appears as product in equation 4. If we add equation 2 and equation 4, we can eliminate the calcium chloride on both sides of the equation and calculate the enthalpy. If we compare the result obtained with equation 1, we can see that we need to remove the chlorine ions, either in aqueous form and as gas. These ions appear in equation 3. The chlorine ion as gas appear as reactant in equation 3 and in equation 2 plus 4, and the aqueous chlorine appears as product in both equations. This means that we need to change the direction of equation 3. Additionally, we have double number of chlorine ions in equation 2 plus 4 than in equation 3, therefore we are going to double the number of ions in equation 3. We can think that we have multiply equation 3 by -2 to get. We add now the modified equation 3 with the equation 2 plus 4 to get. We see that the common terms in this equation are the chloride gas, the aqueous chloride and the water. As we have 2 chloride ions in each side, we eliminate them. The same applies for the chloride gas. On the left, we have 3 molecules of water and 2 on the right. We can eliminate 2 molecules of water on each side and leave 1 molecule on the left. The addition of the enthalpies give us a value of -1566.7 kilojoules per mole. Rounded to no decimal places, it is -1567 kilojoules per mole. Part B of question 5 is about a fuel formed by a 1:1 molar ratio of octane and ethanol. We have 2 questions. In the first question, we are asked to write the equation for the complete combustion of this fuel. As the complete combustion of hydrocarbons and ethanol produce water and carbon dioxide, for a 1:1 molar ration we can write the equation: 1 mole of octane plus 1 mole of ethanol plus A moles of oxygen produce B moles of water and C moles of carbon dioxide. We fix the number of mole of octane and ethanol to 1 and balance the equation. Carbon and hydrogen are provided by the octane and ethanol, so B and C are easy to find. The number of hydrogen provided by 1 mole of octane and ethanol is 18 plus 5 plus 1 equals to 24 mole. As each molecule of water has 2 atoms of hydrogen, we are going to need 12 molecules of water. Therefore, B equals to 12. The number of carbon provided by 1 mole of octane and 1 mole of ethanol is 8 plus 2 equals to 10 mole, that are going to form 10 moles carbon dioxide. So C equals to 10. We finish with the oxygen, counting as atoms. In the reactant we have 1 oxygen provided by the ethanol and 2 provided by the O2. In the products, we have 12 provided by the water and 2 times 10 by the carbon dioxide. If we solve the equation, we get that A equals to 31 divided by 2. Therefore, the equation is 1 octane plus 1 ethanol plus 31 halves oxygen give 12 water plus 10 carbon dioxide. In the second question, we are asked to calculate the energy released, in kilojoules, by the complete combustion of 8 kilograms of this fuel. We are given the combustion enthalpies of the octane and the ethanol. We start by calculating the molecular masses of the octane and the ethanol. For the octane, we have 8 times 12 plus 18 times 1 equals to 114 grams per mole. For the ethanol, we have 2 times 12 plus 6 times 1 plus 1 times 16 equals to 46 grams per mole. A combination of 1 mole of octane and 1 mole of ethanol give a mass of 114 plus 46 equals to 160 grams. As we have 8 kilograms or 8,000 grams, the number of mole of the combination is 50 moles of octane and 50 moles of ethanol. As we are given the enthalpies of each reactant, we can calculate that the enthalpy asked is -5470 times 50 -1367 times 50 equals to -341,850 kilojoules. Question 6 is about vitamin C. In question A, we are given the structure of the vitamin C, that is an optical isomer. We are asked what is the total number of optical isomers with the structure of vitamin C. A carbon bonded to 4 different atoms or groups is an optical isomer. Looking in the structure given, we can find 2 carbons with 4 different atoms or group attached. As each atom has 2 isomers, we have a total of 2 times 2 equals to 4 isomers. You can remember the formula 2 to the power of n, where n is the number of chiral carbons, handy in molecules with several chiral atoms. In part B, of question 6, we have the statement saying that the vitamin C is extremely soluble in water. A vitamin C ester is available in tablet form as a less soluble source of vitamin C. We have 2 questions. In the first question we are asked why vitamin C is extremely soluble in water. The vitamin C molecule has 4 hydroxyl, OH groups, that form hydrogen bonding with water. In the second question, we are given the molecular formula of an ester in a vitamin C ester as C22H38O7. This ester can be prepared by reacting vitamin C with a long-chain carboxylic acid with formula CXHYCOOH, in the presence of an acid catalyst. Vitamin C and the long-chain carboxylic acid react in a 1:1 molar ratio. We are asked to determine X and Y in the formula of this carboxylic acid. The ester formed is going to be between a hydroxyl group, OH, of the vitamin C, and the carboxyl group COOH of the carboxylic acid. We can express the reaction as we know that the molecular formula of the ester is C22H38O7, we only need to count the number of atoms of carbon and hydrogen. In the carbon, we have that 5 plus 1 plus 1 plus X equals to 22. This gives X equals to 22 minus 5 minus 1 minus 1 equals to 15. In the hydrogen, we have that 7 plus Y equals to 38, giving Y equals to 38 minus 7 equals to 31. In part C, of question 6, we are provided with the statement that the vitamin C is a weak acid and its acidity dissociation constant is provided. This part has 2 questions. In the first question, we are given the reaction of protonation of water by the vitamin C and we are asked to add curly arrows to the mechanism provided for this process. Comparing the differences between the reagent and the product, we can see the differences and give us an idea of how to produce the changes. We can see that 1 hydrogen is going to be lost in the vitamin C and a double bond is formed in the oxygen. We also can see that the double bond inside the ring is transferred away from the newly double bond formed, pushing 1 electron to the oxygen with the initial double bond. With these observations, we can think that the water takes the hydrogen using a lone pair of electrons from the oxygen and the electron left is transferred via double bond until it reaches the oxygen. In the second question of this part, the student dissolves 0.15 mole of vitamin C in water and makes the solution up to 250 cubic centimeters in a volumetric flask. We are asked to calculate the pH of this solution of vitamin C, giving the answer to 2 decimal places. To calculate the pH, we need to use the equilibrium constant given. With the number of moles and the volume of the solution, we obtain that the concentration of the vitamin C is 0.15 mole divided by 250 cubic centimeters and multiplied by 10 to the power of 3, to transform the cm3 to cubic decimeters, the concentration of vitamin C is 0.6 mole per cubic decimeter. To simplify, I will call the vitamin C as AH and the acid-base equilibrium will be dissociation of AH to give A- and H+. The equilibrium constant is given by the multiplications in equilibrium of the concentrations of A- and H+ divided by the concentration in equilibrium of AH. I use a table with initial, change and final concentrations for each species to help me with the calculations. The initial concentration of the vitamin C, AH, is 0.6 and the initial concentrations of the other two species are 0. In the change, we have that for X moles of H plus formed, X moles of A minus are formed and we are removing X moles of AH, therefore, it is minus X. In the row labeled as final, we add the columns above, AH gives 0.6 minus X, A minus and H plus, both give X. Replacing values in the equilibrium constant, we get that 7.94 times 10 to the power of minus 5 is equals to X to the power of 2 divided by 0.6 minus X. This is a quadratic equation. It is always good to make the approximation that the X is much lower than the number given, in this case, X is much lower than 0.6 and solve the equation 7.94 times 10 to the power of minus 5 is equals to X to the power of 2 divided by 0.6. This give us that X is equals to the square root of 6 times 7.94 times 10 to the power of minus 5, that it is 6.902 times 10 to the power of minus 3. The approximation that X is much lower than 0.6 is correct here. The concentration of protons is 6.902 times 10 to the power of minus 3. Taking the logarithm and changing the sign, we have the pH equals to 2.161. Rounded to 2 decimal places, it is 2.16. In Part D of Question 6, a student carries out an investigation to find the vitamin C content in 150 cubic centimeters of orange juice. The student titrates the orange juice with iodine and we are given the reaction. When there are many dilutions and volumes involved, I find useful to draw a diagram with the dilutions involved in each step. The student dilutes 150 cubic centimeters of the orange juice with water to 250 cubic centimeters in a volumetric flask. The student then titrates 25 cubic centimeters volume of the solution with 9.6 by 10 to the power of minus 4 mole per cubic decimeter iodine solution. The mean titer of iodine is 22.50 cubic centimeters. We are asked by the mass, in milligrams, of vitamin C in a 150 cubic centimeters serving of the orange juice. With a concentration of 9.6 by 10 to the power of minus 4 moles per cubic centimeter, a volume of 22.5 cubic centimeters gives 2.16 to the power of minus 5 moles of iodine. The stoichiometry of the reaction indicates that the 1 mole of iodine reacts with 1 mole of vitamin C, therefore, the student have 2.16 to the power of minus 5 moles of vitamin C from the 25 cubic centimeters used. As these were from 250 cubic centimeters of solution, in the 250 cubic centimeters of solution we have 10 times more, that is 2.16 to the power of minus 4 moles of vitamin C. These moles were provided by the 150 cubic centimeters of orange juice. Remember that diluting from 150 to 250 cubic centimeters with water changes the concentration, but not the number of moles. As we are given at the beginning of the exercise 6, the formula of vitamin C as C6H8O6, we can calculate that the molecular mass of the vitamin C as 6 times 12 plus 8 times 1 plus 6 times 16 equals to 176 grams per mole. Multiplying the 2.16 to the power of minus 4 moles of vitamin C by its molecular mass of 176, we obtain 0.038016 grams of vitamin C. When expressed in milligrams, we get 38 milligrams per 150 cubic centimeters serving. And this is the end of the paper. If you want to see more videos like this, please click like, and leave a comment, as it will help me to carry on making more videos.